ladies and gentlemen. This presentation is about detailing of reinforcement. It refers firstly to the work of designers and drafting personnel in structural design offices. It also recognises the importance of the work done by designers and detailers working on construction sites. Let us look at a couple of very different examples from building projects. This slide shows a simple cross-section through a slab and wall. The notes 1 to 4 are intended to show how the lines on the drawings must always be considered in terms of the interrelated construction processes of erecting formwork, placing reinforcement and placing concrete. In particular, this slide shows the importance of thinking through the potential problems at the construction joints. This should be done as early as possible in the design process so that their location is compatible with requirements for all the other processes. Please don't worry about trying to pick up too much detail from these slides. By the time I am finished, this presentation, including my spoken notes, should be uploaded onto my website, which is referenced in the published paper. The notes should give enough additional information for you to understand what the slides are trying to say. Looking at this layout, I would imagine that the designer would have had great difficulty in keeping a clear picture of where all the bars were going. Problems with interfering bars might be discovered by the reinforcement scheduler when he started drawing up cutting and bending lists for the subcontractor supplying the steel. However, many of the interfering bars and the areas of serious congestion are often not discovered until the steel fixers start to actually assemble the bars. This is a bird's eye view of the construction site. It is hard to imagine that there weren't a lot of bars which couldn't be placed as the designer intended. Where reinforcement is very congested or where bars intersect in the same plane, some bars must be displaced and sometimes even cut. Where bars are cut, then a welded splice is often needed to restore continuity. However, it is not easy to ensure that field welds develop the strength and ductility of the original bar. This could be a major source of potential disaster. For example, where starter bars from piles may be cut to make room for horizontal bars in the pile cap. The main picture, 3, looks down into the cage for a pile cap. The yellow arrows show horizontal bars which have to be threaded through the exposed starter bars where the concrete has been stripped back from the heads of the piles. However, a close look at the tops of the piles in picture 2 will show that the piles may be displaced and twisted out of their planned position as they are driven into the foundation material. The reinforcing in such pile caps is often much more congested than in this example. When piles are seriously out of position, the designer may have to be consulted to come up with some alternative Rio bar arrangements so that the design requirements can still be met. These problems may be solved satisfactorily on a bridge contract where there is a high level of supervision and inspection. However, on some building sites there is not good supervision, and unapproved and unreported omission or cutting of bars could significantly reduce factors of safety. What I call proactive reinforcement detailing is when the designer takes the initiative by thinking about potential construction problems and then tries to minimise them by appropriate detailing of the reinforcement. However, even if the designer has built in some avoidable construction problems, there is still an opportunity for the constructor to be proactive by studying the drawings well in advance of construction so that he can have any unsatisfactory details changed by the designer before any bars are cut and bent. This presentation is intended to help inexperienced designers to think construction and to encourage them to become good reinforcement detailers. The structural designer determines how much steel is required in each cross-section of a member, and he usually decides on the sizes and spacings of bars. However, when the actual bars are bent and placed, the steel fixers often find that there is interference between bars, so that they can't be placed where they should be. Furthermore, the concreters often can't get proper access to insert pumps and vibrators, and to observe the concrete being placed and compacted. Surface finishing operations can also be unnecessarily difficult. Proactive reinforcement detailing will prevent such problems from occurring. In my opinion, the job of a reinforcement detailer is to convert the designer's structural requirements for each cross-section of a member into bar shapes and sizes which can be assembled together so that the planned layout in all cross-sections is achieved without bars interfering with one another or with the effective placement and compaction of concrete. All reinforcement is designed to be surrounded by good concrete. That means concrete with the required design properties of bond strength and durability and fire resistance, etc. However, the hardened concrete we see when the formwork is stripped was originally fresh concrete that was placed inside the reinforcement cage and then made to flow through the cage until the formwork was completely filled. Obviously, that didn't happen in this major foundation element. The reasons for this problem were complex, but it's fair to say that some proactive reassessment of design and construction requirements might have prevented it. The next 3 slides give an example of proactive reinforcement detailing. The arrows at the top are meant to represent those items of equipment that must be able to reach effectively down to the bottom of the pour. Blue is for the pump hose, green is for vibrators, and yellow is for light. Don't forget, it's very dark inside the cage once the side forms are in place. I can only assume the top steel is too congested to allow concreters to get inside the cage. The pump hose must be inserted to the bottom of the cage so that the concrete can be observed moving outwards from each discharge point and working its way around all reinforcement bars so that each layer of bars is fully encapsulated before fresh concrete is deposited on top. In particular, it must be possible to continuously monitor the concrete in the cover zone as it rises up the space between the cage and the formwork. The first place I want you to look at is the lower section of the cage where the openings in the outer steel layer are big enough and close enough to allow concrete to flow freely into the cover zone. Up to this level, the cover zone should be completely filled with homogeneous concrete, having the same properties as the core concrete. However, from that level and right up to the top of the pour, an additional set of bars has been added. These are indicated by the thin vertical red arrows. Even under intense vibration near the inside of the cage, only cement slurry or mortar could force its way through the narrow gaps in what is almost a solid wall of steel. These extra bars, together with the closely spaced and lapped horizontal stirrups, have greatly restricted the access for concrete to flow outwards into the cover zone. 2 small windows between each set of stirrups is all that allows the concrete to get through. In practice, the flow of concrete into the cover zone would have to be observed very thoroughly from the top of the pour. Even with well-directed lighting, it would not be easy for an inspector to verify that compaction had been achieved consistently throughout the cover zone. Of course, once the forms were stripped, it should be fairly easy to locate the voids. However, it is not so easy to do an effective repair job on such voids.